In this video, we will derive the energy of an electron in an orbit and the energy difference between two orbits. Derivation of energy of an electron in an orbit. We know that the electron can possess both the kinetic energy and potential energy. Kinetic energy of an electron is due to its motion in an orbit, while the potential energy of an electron is because of the attraction with the nucleus. So if we want to calculate the energy of an electron, we will sum up both the kinetic energy and potential energy. And we know that the kinetic energy is equal to half mv square. M is the mass of electron and v is the velocity of electron. While potential energy is equal to the work done in bringing the electron from infinity. Infinity here means that the electron is present at that point where there is no interaction between electron and nucleus. And this electron will bring to a point where there is interaction existed between the electron and nucleus. So for this process a work is done that is equal to potential energy, and that has formula minus force divided by distance. So force here is force of attraction between the electron and nucleus that we already calculated according to the Coulomb law, that is equal to Ze square divided by 4 pi epsilon naught r square. So we will put this value of force in the above equation. So potential energy is equal to minus Ze square divided by 4 pi epsilon naught r square multiplied by distance that is in r. So here the r and r square, here r and here 1 r from this square will cancel out, and we will get potential energy is equal to minus Ze square divided by 4 pi epsilon naught r. Here the negative sign in this formula indicate that the potential energy decreases when the electron is brought from the infinity to the point where there is an interaction between the nucleus and electron. Now putting the value of kinetic energy and potential energy in the formula, that is equal to kinetic energy plus potential energy, we will put their values. Kinetic energy has formula half mv square plus potential energy has formula minus Ze square divided by 4 pi epsilon naught r. Now here the plus and minus will result in minus, so the formula is half mv square minus Ze square divided by 4 pi epsilon naught r. Now substituting the value of mv square, that is equal to Ze square divided by 4 pi epsilon naught r in the above equation, this one, we will get half Ze square divided by 4 pi epsilon naught r minus Ze square divided by 4 pi epsilon naught r. Now here if we solve it, if we take this term as common, that is Ze square divided by 4 pi epsilon naught r, this is taken as a common, and here it is half minus, here it is 1, so we will write it as half minus 1. Half minus 1 will result in minus half. Here we will put minus sign because the minus sign in the above equation will be is with bigger value or larger number. So the formula is minus half Ze square divided by 4 pi epsilon naught r. Now here the 2 and 4 will multiply and it will result in 8. So energy is equal to minus Ze square divided by 8 pi epsilon naught r. Now putting the value of r from this equation, that is n square h square epsilon naught divided by Ze square pi m in equation of energy, that is equal to Ze square divided by 8 pi epsilon naught, and here we will put R value from this equation into this equation that is highlighted with red color, that is the value of R. Now the values that are the denominator of a denominator will move towards the numerator side. So the equation is Z square. See here the Z square pi m will move to the upper side. So Z square pi m divided by 8 pi epsilon naught n square h square epsilon naught. So all these value will be in the denominator, and this value will move towards the numerator side. Now here two z are present, so z will become z square, e square and e square, so it will become e4. M is present and the pi is present in the numerator and denominator, so it will cancel out. Here these both terms will also square, so we will get minus z square e4 m divided by 8 n square h square epsilon naught square. Now for nth orbit, for any n orbit, we will get z square e4 m divided by 8 n square h square epsilon naught square. It is for nth orbit. And here we will know that e4 m 8 h square epsilon naught square, all these are common term, and only the change value in this equation is z square and n square. Z is the proton number and n square is the number of shell. So these values are different, so we will separate these value and all the other common terms are combined. Now for hydrogen atom, Z is equal to 1, so we will put the Z value as 1. Z square is equal to 1, so we will put here 1 divided by n square, and the other formula remain the same. Now we know that all these values are constant, so if we put all these numerical values, we will get 2.18 multiplied by 10 to the power minus 18 joule per atom. And the above formula is, here we will put this value in the above formula, minus 2.18 into 10 to the power minus 18, and 1 divided by n square is present in this formula. It is quite simple. Collect this value as 2.18 into 10 to the power minus 18 and put this value in the above formula, that results in this formula. Now here is joule per atom. If we convert this formula into kilojoule per mole, we know that if we convert joule into kilojoule, then we will divide it by 1000, and we know that 1 mole has Avogadro number of atom, so we will multiply it with Avogadro number. So in terms of kilojoule per mole, the formula is En is equal to minus 2.18 multiplied by 10 to the power minus 18, 1 divided by n square, 6.023 into 10 to the power 23 divided by 1000 kilojoule per mole, while in joule per atom the formula is 2.18 into 10 to the power minus 18, 1 divided by n square joule per atom. Now if we multiply this term with this term and divide by 1000, we will get 1312.36 divided by n square kilojoule per mole. If we take it as an E1, E2 and E3, we can calculate the energy of each orbital if we know that its principal quantum number, that is 1, 2 or 3. So N1, that is known as ground state, N2, N3, N4 and so on, these are known as excited states. So we will calculate the energy value for E1, that is equal to minus 1312.36 divided by n square. For E1, the number of shell is 1, So here we will put 1 square and it will result in 1312.36 kilojoule per mole. For E2 we will take here as N2, so 1312.36 divided by 2 square and we will get 328.32 kilojoule per mole. Now the energy difference between two orbits. This is the formula of energy that we derived earlier. Now E1 is the energy of orbit N1 and E2 is the energy of orbit N2. Then the above equation can be written as E1 is equal to minus E4 m divided by 8 h square epsilon naught square z square divided by N1. Here it is E1, so we will put it as N1. This is for lower energy orbit. Here for E2 we will put N2 and N2 is a higher energy orbit. Now we will put the value of E2 and E1 in delta E formula. We will get minus E4 m divided by 8 h square epsilon naught square z square divided by N2 square plus, because here the minus and minus will result in plus, E4 m divided by 8 h square epsilon naught square z square divided by N1 square. Now there are some common terms, that is z square E4 m divided by 8 h square epsilon naught square. These terms should be kept outside the square bracket, and the term that are changed is only the number of shell or number of orbit, so it should be kept inside the square bracket along with their sign. Now here it is plus, so we will move it to the start side, so it will 1 divided by N1 square, and it has minus sign, so it will move to the inner side, that is minus 1 divided by N2 square. Now we know E4 m divided by 8 h square epsilon naught square is equal to 2.18 into 10 to the power minus 18 joule per atom. So putting this value in the above equation, delta E is equal to 2.18 in 10 to the power minus 18, 1 divided by N1 square minus 1 divided by N2 square joule per atom. And if we calculate this value in terms of kilojoule per mole, then the formula is 1312.36, 1 divided by N1 square minus 1 divided by N2 square kilojoule per mole. So these are the two formula for delta E in terms of joule per atom and kilojoule per mole.